All right, hello everybody, and welcome back to session 5 of Beginner Competitive Programming. Today we are going to be talking about trees, which is a continuation of graphs from last time. Okay, so on the agenda today, first we're going to start off with a little recap of graphs just to get everyone refreshed, freshen up on graphs. And then we're going to take a little detour and talk a little bit about hash maps and how they could be useful for graph theory. Then we'll actually get into talking about trees, talking about what exactly a tree is, going into specific type of trees, like specifically a spanning tree. We're going to do a little recap of BFS and DFS as we go along. And then we'll have one contest problem, then start talking about minimal spanning trees, go into Prim's algorithm, have one more example problem before we get into our contest. So definitely a lot today. So hope everyone's ready. Okay, so here's our little recap on graphs. Let me know if I go a little quickly. I'm assuming everyone here has already seen the graphs presentation, but if you guys need me to go a little slower, then just let me know. Okay, so what is a graph? In graph theory, a graph is a set of vertices and edges representing relationships between objects. We usually represent vertex as dots and then edges as lines between those dots. And you can represent turns out you can represent a lot of different things with graphs. And so here's some more terminology. Adjacent vertices are vertices connected by an edge. Since there's an edge between these two vertices, they're adjacent. And degree is talking about how many edges a vertex has. So this vertex has a degree of 1. This vertex has a degree of 3. Degree isn't that important today, but it's definitely something you should know. And there's also the idea of paths and cycles. So a path from A to B is just a sequence of vertices in a graph that starts with A and ends with B. So for example, A, C1, C2, C3, C4 to B. And then a cycle is very similar. It's just a path where the starting node, I'm going to say node a lot. I prefer node over vertex. So the starting node is the same as the ending node. So A, C1, C2, C3, C4, C5, and then back to A. That's an example of a cycle. These are all pretty intuitive examples. And of course, there are a few ways to actually store a graph, and the two most common ones used in competitive programming are an adjacency list and adjacency matrix. These two both have their pros and cons, but today we'll mostly be using adjacency lists, since I think these are the more popular and honestly easier to implement and take up less space. So we'll be using adjacency lists today. Okay, and there's also the idea of a weighted graph. This was mentioned in the last presentation. However, it's going to play a really big role in today's workshop. So in a weighted graph, each edge is assigned a weight, and they can be directed or undirected, but the important is the weight of the graph. So edges store a bit of extra information. They have a number associated with them, which is the weight. And these store a little bit of extra information, which we may want in certain types of graphs, as you'll see today. And the implementation of weighted graphs are pretty similar. Instead of storing just the edge, just the adjacent node, you also store the weight of the edge along with that node. So for example, 152 means 1 is adjacent to 2 with a weight of 5. And then 113 means 1 is adjacent to 3 with a weight of 1. So that's all we have that's generally all you need to know from last workshop to get started with learning about trees. But before we do that, let's take a little detour and talk a little bit about hash maps. Okay, so we know how to store graphs like this. We're very experienced with storing graphs that look very similar to this. So every node is labeled like 1 through 6. It's very simple, like ordered. We can use a vector to store like the adjacency links pretty simply like this. So we could use a vector and index like into 1 to get wherever 1 is adjacent with, and same thing for 2, 3, 4, 5, and 6 because they're all in order. It's a like a sequential numbering of the graphs. But what if we want to store a graph that looked something like this? We can't use, these are, as you can see, decimal numbers. We can't necessarily use decimal numbers to index into an adjacency list or the one that we've learned so far. Like, what exactly will we put into here? One idea I sort of thought of was you can multiply everything by 10 and then have a giant vector, but it's honestly using way too much space and would be very wasteful. So is there a simpler way to do this? What if instead of decimals, you just straight up had strings? So every node is labeled with a name that is a string. How exactly would you represent this in an adjacency list, like indexing through this? So hopefully you can see the problem here. We want a way to generalize an adjacency list so that we can index nodes of different types. For example, if I want to create a graph where all the nodes represented the like ICPC officers, how exactly would I want to index into, for example, Alvin or for example, Raya? Is there any data structure or way that we could do this? Oh, it turns out, yes, there is. We can use this new data structure, probably one of my favorite data structures, a hash map, to accomplish this. Okay, sorry, one sec. Okay, so a hash map is a data structure that holds the key value pairs. So when you insert a key value pair, you can later use the key to access its value, which may not seem like something that important right now, but turns out it really is. And it may be a bit confusing. It may be a bit confusing like hearing that definition. So I think the best way to learn about what a hash map actually does is to start using it and looking at examples of its uses. So here I initialize a hash map, which C++ calls an unordered map. And so initializing, you do unordered map, string, string, and then whatever name you want it. I'm just choose map. And this means you want a string as a key. You want the key to be a string type and you want the value to be a string type. That's why I have 2 strings right here. And so let's start using it. I can say I want to insert the key value pair Nguyen Alvin. Nguyen is my last name, and I want the value to be Alvin. And so we store it here inside our hash map. And then we can do the same thing with Xia and Tony. So Xia is the key, and then Tony is the value. And then later, if I have just the key, I can put it into the map and get its value out. One important. Is there a question?
Yeah, I have a question about, so does that mean like only one key can, where like one value can get assigned to one key, or is there like any way to do more than one?
I'm gonna there's one way you can have a key mapped to multiple values. Is having your value be a vector
Oh,
or basically a list. But in general, what I was actually going to get to this. A key can generally only have one value. So for example, if I then said, oh, I want to map the key Xia to instead Lucas, it would get rid of the key value pair Xia Tony and then replace it with Xia Lucas.
I see. Thank you.
No problem. Okay, and then you can also do find. Find is a bit weird with HashMap because it uses the C++ uh, like tool called iterators. I'm not sure if you guys have learned iterators yet, but what you do is map.find and then whatever key you want to find. For example, I use Zhang, and it should return an iterator. Uh, if you don't, it should return an iterator to one of the key value pairs. You can think of iterator as kind of like a pointer. It's a bit different, but if you want to think about it simply, just think about it as a pointer. However, if you don't find the key inside the map, it'll give you the end iterator, which is generally just means you didn't find it. It needed to return an iterator, so it just returned the end iterator, which doesn't really point to any key value pair. So if I do map.find Zhang and it equals map.end, this means I couldn't find the key Zhang inside of this hash map. So this would return true. And then you can, of course, do your access. So if I want to get the value of the key Nguyen, I'd just do map Nguyen and it would return Alvin. And then do the same thing for Xia, and then it would return Lucas. And then, of course, you can delete key value pairs. So if you say erase Nguyen, it would delete my name from the hash map. And if you did erase Xia, it would delete the other name. Oh, did someone say something? I don't see an app for that. You'll need to download that. Oh my gosh. Okay. Siri just started talking, and apparently I thought someone was talking on Zoom. But anyway, here is just a cheat sheet of what we just went over. This is just a general summary if you want to use hash maps later. I'll give you guys a few seconds to look at it. Okay, so I hope you guys have had a good look of how to use hash maps. This is great and all, but how exactly do we use a hash map to create our general adjacency list? Well, as I talked about earlier when I was answering the question, you can have your value be a vector of values, essentially. So, for example, if I wanted a node that has where if I wanted to have a graph where every node was represented by a string value, I could do unordered map with the key being a string and then the value being a vector of strings. And then I can just do our inserts. So first if I want to insert eggs as a node into this graph, I would do adjacency list eggs and then set that into an empty vector. And then I could just push in values like it's an adjacency list. So here inside eggs, I push in ham. So eggs is now pointing to ham. And then I can do the same thing for pancake. And then set pancake to point to waffle. And then, yes, I'm saying I'm pushing like syrup into pancake, like pancake's adjacency list, and then pushing milk into eggs adjacency list. So as you can see, we can generalize our adjacency list not to just be 0 through n or 1 through n. We can now like actually name our vertexes, which may be very helpful. This will be very helpful in the future. Okay, so that's enough for that detour of hash map. Let's actually go into talking about trees. So what exactly is a tree inside graph theory? It's pretty simple. So in graph theory, a tree is just a connected acyclic graph. Connected means that you can reach like any node. You can reach any node. You can go from one node to another. Like if you choose any two nodes, there's always a path from there to there. And then acyclic means there's no cycles. So if you look at this example, it's connected, there's no cycles. We call this a tree. Okay, so let's do a little mini exercise and talk about, is this a tree? I'm gonna give you guys a bunch of graphs and you guys are gonna tell me, is this a tree or not? So this first one, is it a tree? I'll give you guys maybe like 5 seconds. Anyone want more time? All right, sweet. This is not a tree because it is not connected. What about this graph? Is this a tree? Yes, it is a tree because it's connected, and as you can see, there are no cycles. Is this a tree? Again, yes, it is because it is a connected graph and it has no cycles. And we can keep going. We'll go a little faster now. This is, I'll give you guys a few seconds, not a tree because though it's connected, there's a cycle. So you could go from here to here to here to here, all the way back. So that's a cycle. We want trees are acyclic, so this is not a tree. And this last graph right here is connected, doesn't contain any cycles. It's also a tree. And so it turns out trees appear a lot more than you'd think inside just graph theory and like in real life. So for example, here's an example of a type of tree. You could see here's just a random tennis tournament where every vertex represents like the outcome of a game, and then every edge represents like where essentially a match. And so you can represent a tennis tournament or any type of tournament using a tree. You can also represent an administrative hierarchy or in general any type of hierarchies with a tree, since they follow this type of branching, no real cycles, everything is connected type idea. So this is a tree. And there are definitely a lot of other examples besides these. One that I thought of and don't actually have on the slides is a file structure. So how you organize your folders and files on a computer is definitely it in a tree structure as well. Okay, so now we're just going to go into some useful tree knowledge. And so this is going to be a little bit theoretical, but let G be any graph with n vertices. And then any two of the following imply the third. So I'm going to list 3 bullet points and then talk a little more about the sentence. So let's say G is connected, G is acyclic or doesn't have any cycles, and G has n minus 1 edges. So if any of the two following apply, so if G is connected and G is acyclic, that would imply G has n minus 1 edges. If these two were true, so if G was connected and G has n minus 1 edges, then G is acyclic. So 2 of these implies a third, which is definitely something useful that you should know about trees because, well, recall that a tree is a connected acyclic graph. So what exactly does this mean? I talked about this here. A connected graph with n vertices and n minus 1 edges is a tree since it's acyclic. An acyclic graph with n vertices and n minus 1 edges is a tree because it's connected. And probably most importantly, a tree with n vertices has n minus 1 edges because a tree is connected acyclic. That means it has n minus 1 edges. So any questions so far? All right, sweet. Let's keep going then. And let's talk a little bit about spanning trees. So a spanning tree is a subgraph of a graph that is a tree and includes all vertices of this graph. And I have a little visual example right here. This is just a regular old graph. It's not a tree or anything. And let's say we take these reddened edges and then turn them into its own graph. Notice that it includes all the nodes of the original graph. And it's also a tree because it's connected and doesn't have any cycles. So we would call this a spanning tree of this graph. And so when does a spanning tree actually exist? If I just gave you some random graph, could you tell me if a spanning tree existed or not? For example, does a spanning tree exist for this graph?
No.
All right, yeah, good. There is no spanning tree for this graph because we expect a graph like wanted to contain all of these vertices. It would have to be a tree that would be connected because trees are just connected, and this graph isn't connected. And then for this graph, is there a spanning tree?
Yes.
Good job. Yes, there is a spanning tree for this. If we just took this edge, this edge, this edge, this edge, and this edge, that would be a spanning tree. And there's a few more examples, but that was just one I thought of off the top of my head. So yes, as you can see from these two examples, a graph has a spanning tree if and only if it's connected. And like, why is this the case? So if a graph has a spanning tree, there's a path from any vertex to any vertex because trees are connected and a spanning tree containing all the graph. A spanning tree containing all the vertices of the graph will make the graph connected, essentially. And if a graph is connected, we can just delete some edges from the graph to create a tree that includes like all the vertices of the graph and essentially be a spanning tree. So for example, if I deleted this edge right here, what would be left would just be a spanning tree. So the important takeaway here is that a graph has a spanning tree if and only if it's connected. So if it's connected, has a spanning tree. If it has a spanning tree, it's connected. Okay, so that's all well and good. However, how exactly do I go about finding a spanning tree of a graph? To do that, we're going to need an algorithm that traverses through the edges so as not to visit a vertex twice. And do any algorithms come to mind for this? It's, I'll give you a hint. It's something that's we've learned very recently, if you've been attending or watching our workshops.
BFS and DFS.
Yeah, good job. So it turns out that BFS and DFS help us generate a spanning tree. And so I'll give you guys a little bit of recap on like BFS and DFS if you don't completely remember what they mean. So, and a note, graph can have more than one spanning tree. So in BFS, or breadth first search, we start at some vertex and explore all adjacent vertices, and then explore all of their adjacent vertices, and so on. So it's essentially going level order, starting at just some vertex. So we start at 1, and then we go to all of 1's. We go to all of 1's neighbors, which would be here and here. So that now we have 2 and 3. We go to 2 and 3's neighbors then. So that would be this node, and this node. So we'd go 4, 5, and 6. And then for DFS, we start at some vertex. We explore as far as possible along some branch, and then backtrack once we can't explore anymore. So if we run BFS going this way, starting this way, we'd go 1, 2, 3, backtrack back to 1, and then go down 4, go up 5, backtrack 6, and then we'd finish. So we'll just run through the slide. 1, 2, 3, backtrack back to 1, 4, 5, backtrack to 4, and then go down to 6. Okay, so that leads us here to our first problem, which is fire trucks are red. Since there's only a few of us, I'll be asking guys like how long you guys need as we go along through this, as you go along and like try out this problem for yourself. Okay, so like just a general summary of the problem. So you're given n individuals and they're associated with certain numbers, and you want to know, you're asking, is it possible to indirectly relate all the individuals by their associated numbers using only n-1 direct relations? So a direct relation would mean if I was associated with a number 2 and someone else was associated with a number 2, then we're directly related. Is it possible to relate everyone in this like giant like relation of numbers? And so the strategy for this is to essentially look at each number, like each individual, and then each number associated with that individual. So we'll call the individual I, and then for each number n associated with I, if we haven't seen n before, we want to remember that n is associated with I. And then if we remember seeing n associated with some other individual j, then I and j are related by n, which makes sense. Again, a bit abstract, so we're going to go over the sample input and see exactly what I mean. So let's start off with the input, like individual 1. You can see 2 means there's 2 numbers that like are associated with 1, 17 and 10. So we remember that 17 is associated with 1, 10 is associated with 1 as well. And now we move on to vertex 2. we haven't seen 5 before, so we want to remember that 5 is related to 2. And then we get to 10, and then we see 10 is already like associated with 1, so we're going to relate the 2. We're going to relate the 2 with the number 10. And so now we go down to vertex 3. Vertex 3 is associated with 10. 10 is already associated with 1. We relate the 2 with index 10. We haven't seen 22 before, so remember that 22 associated with 3. Go down to vertex 4. 4 is associated with 17, already associated with 1. Relate the 2 with 17. Relate 3 and 4 with 22 because 22 is already associated with 3. And then we remember that 9 is associated with 4. And then we keep going. So that was 5, and now we go to 6. And there we go. We've looked at all the individuals and all the numbers they're attached to. And we've built up these 2 pretty strange structures. We can look at this top one and see, yeah, this is a weighted graph. But what about down here? Does anyone know? Does this like data structure look familiar at all? It's not necessarily an array, right? Because you index 17 into 1, but these numbers aren't actually in order. So what exactly could this be? Turns out it's a hash map, the thing that I talked about earlier. And so we used a hash map and like a directed graph to like get our relation. So it turns out that a hash map and a weighted graph might just be able to help us solve this problem. And so visually, we can see that all the individuals are like directly related by their associated numbers. So there's not one individual that's not a part of this giant relation. But how do we check this algorithmically? Well, we can use either BFS or DFS to check if the graph is connected. And then recall that if a graph is connected, then it has a spanning tree. And also recall that a tree with n vertices has n-1 edges, which is coincidentally the number of edges we need in our output. So if there are like n individuals we're essentially outputting n-1 relations, or in this case, n-1 edges of our graph. So combining all of these facts, we can run BFS or DFS and attempt to construct a tree. And if we add n-1 edges to a tree, then we have a spanning tree, and that's essentially what we want to output. And this is what the problem boils down to, is trying to find a spanning tree inside of essentially a graph that they give you. And so let's just run BFS because I kind of like BFS. I kind of prefer it over DFS. So we'll run an example BFS on the graph that we constructed. We'll start off at 1. We'll go down to 2. And so we will write down 1, 2, 10, and then go down to 3. And then we write 1, 3, 10. Go down to 4. We write 1, 4, 17. Go to 5, and we have 1, 5, 17. We're finished with 1, so we go down to 2. It's not adjacent to anything else, so we go down to 3. 3 is adjacent to 6, so then we do 3, 6, 22. And essentially, we have our spanning tree. But how could we tell if it was a spanning tree if we didn't have this visualization? We can actually look, if you remember like the useful facts about trees from earlier, we can actually look at the number of edges that we wrote down. So notice there's 6 nodes or 6 vertices and 5 edges inside the tree, which means we have a spanning tree. So this would we want to output this, and this would give us like a correct answer. If we had another example, but like 2 wasn't related to 1, or 2 wasn't related to anything, so it's not a connected graph, we could run BFS on 1 and then get 1, 3, and then 1, 4, 17, 1, 5, 17, and then 3, 6, 22. And then our BFS run from 1 would be over. And then we can check the number of edges again. There's still 6 nodes, but instead there's only 4 edges in our tree, meaning we don't have a spanning tree since the graph isn't connected. So instead we just output impossible. And so that's essentially how you figure out how do you do this problem. And so now we're ready to write this in code. So first we construct the graph to run BFS on. We grab n, and then we get our adjacency list. We create a map, and then we run through each individual, run through each of their associated numbers. And then if we haven't seen it yet, this is if you haven't found like D, which is the associated number, then you remember that it's associated with individual I, and if you have seen it before, then you add it to the graph. I do like 2 adds to make the graph undirected here. And then next we run BFS and DFS. This is like code basically taken from last workshop, so I won't go over too much. But essentially you declare a visited vector of booleans for like the vertexes you visited, and then you use a Q. And so you get like the adjacent vertex and the weight, which you want to store for the output. And one thing that you should notice is that I'm actually not printing out like the edges right away. I'm actually storing them inside this output vector. So whenever we visit a new vertex, I just store like the edge onto the output vector. And that is because of this next step where I have to check if the output is valid. So I want to check if there's, for a graph with n vertices, I want to check if there's n minus 1 edges. And since each edge is represented by 3 numbers, I do 3 times n minus 1. If the output size isn't this number, then we don't have a spanning tree, and then we print out impossible. Else, then I just print out the entire output vector. And you combine all of that, and that is the solution. Okay, so I hope that was fun. Hope that was fun for you guys. Let's move on to another topic, or a related topic, and talk about minimal spanning trees. So a minimal spanning tree, as you can probably guess, is a spanning tree whose sum of the weights is a minimum. And one thing I forgot to add here is that it is talking about a weighted graph. So here we have a weighted graph, and you can see that the reddened edges form a spanning tree. And moreover, maybe you could sort of notice it, but if you add the weights of all the edges inside of the spanning tree, they're like the minimum possible. So you can't find another spanning tree. You can't find a different spanning tree that has like a smaller weight than this one. This is the minimum spanning tree. So does anyone have any questions about this definition? No questions? Okay, cool. So it sort of begs the question, how do we find the weight, or in fact, just find a minimal spanning tree? Well, first we'll start off with just finding the weight. We can't actually use BFS or DFS anymore to get like a minimal spanning tree, because BFS and DFS, as we talked about before, they just usually output for a connected graph just any spanning tree, not necessarily the one with the smallest weight. So if we want to find the minimal spanning tree weight of a connected graph, we're going to need an algorithm that takes into account like the weights of each edge and includes them in the spanning tree accordingly. And so there's actually two main algorithms that we can use to find the minimum spanning tree, but today we're only going to cover the one that's like easier to understand and easier to implement. And that would be Prim's algorithm. Yes. So Prim's algorithm constructs the minimum spanning tree by like iteratively adding edges from a connected graph to like a tree that you construct until it becomes a spanning tree. And so the main idea of Prim's algorithm is that you want to begin at any vertex, which you call the root of your tree, and then at each iteration, essentially add the minimum weight edge adjacent to a vertex that isn't inside of like the tree that we're constructing and isn't adjacent to like another, that isn't adjacent to another vertex in our tree. So this sentence is a bit of a mouthful, but I actually think Prim's algorithm is like pretty easy to understand if you look at it visually. So we're going to go over a demonstration of Prim's algorithm. So this is the graph that we've seen before. This is just a regular weight rated graph, and we're going to run Prim's algorithm on it. So first we want to just choose a root. So we'll choose this vertex right here, and we look at all the edges that are from like a darkened vertex to like a lightened vertex. So it would just be these three, the ones that are labeled with numbers. And Prim's algorithm says we take the minimum edge, like the minimum weight edge. So that would be 3. And 3 leads into this vertex, and now this vertex now becomes part of our tree. And then we keep going. We grab all the edges that are from a darkened vertex to a lighter vertex, and we grab all of them, take the minimum one, which in this case would be 5, and then we keep going. And we keep going. 2 is the minimum here, so we include 2. Now 7 becomes the minimum, so we include 7, and then we include this vertex. 1 is the minimum edge. 4 is then the minimum edge. And then 9 becomes the minimum edge. And after that, we have essentially gone through and we have no more edges that we can look at, which means we are done. We have a spanning tree. And not only that, it's the minimum spanning tree. If you look at all of the weights, if you just sort of look at the graph like all together, you can sort of see, yes, this is definitely the minimum spanning tree. So does anyone have any questions on the demonstration we did on Prim's algorithm? It's really important that you guys like sort of understand how the algorithm works before we get into like how we implement it, since implementing is a bit more tricky. Okay, sweet, no questions. Let's move on to programming Prim's algorithm. So there's 2 important things that we need to keep track of. One, the vertexes we have already visited, or in like the demonstration, I call them the darker vertexes, the vertices, and then like which weighted edge we want to add next to our like constructed tree. And so to keep track of like which edges we have visited, or like which vertices we have visited, we will use a vector boolean similar to how we did for BFS and DFS. But figuring out which weighted edge we want to add is a bit tricky. So in Prim's algorithm, we first want to check if we can add like the minimum weight edge. So we need some data structure that figures out the minimum weight edge like efficiently. And is there even a data structure that does that? Turns out, yes, there is. It exists. And we call it a min heap. Okay, so a min heap is like a specific type of priority queue, and a priority queue is very similar to a queue in where you essentially push elements onto like a queue, and then and then you pop the queue, and it will give you like the element that for a queue is like is first in, first out, I believe. But for a priority queue, it's a bit different. Whenever you pop from priority queue, it'll always be the element that has the greater priority. And in the case of the min heap, that means the number that is the least. If we were to do a priority queue of ints. So this is how you initialize a min heap. The syntax for here is a bit weird and kind of long, but essentially it's saying I want a priority queue of ints, and we're gonna implement it with like a vector. And then this sort of are the comparison function Rohit was talking about in the first lecture. This is talking about like, this is comparing like greater than. It's kind of weird since greater than, you expect this to be like a max heap or where the largest number is priority, but it turns out no, the smallest number has priority. And so let's start pushing into our min heap. So if we push in 4, then now we just have 4 inside of, oh, okay. We have 4 inside of our min heap. And then if we push in 2, 2 is actually going to have more priority than 4, so 2 will be on top. So now we push in 2, and 2 is on top. If we push in 1, since 1 is less than 2, 1 is going to have greater priority than all of them, and so 1 is going to go on top. So if we push in 1, 1 here is on top. And last, we're going to push in 3, and 3, because it doesn't have like as much priority as 1, because it's greater than 1, and it's also greater than 2, but it's actually less than 4. 3 is going to go in between 2 and 4. So this is how our priority queue looks. If we take the front element, or essentially the top, that's basically the element with the most priority. In this example, that would be 1. And if we do pop, it grabs the highest priority element and removes it. So that removes 1, and now 2 is on top and has the most priority. And of course, you can also check if your min heap is empty, which it returns false just because it's not. So this is a little cheat sheet for min heap. This is going to be the primary data structure that we use to implement Prim's algorithm. I'll give you guys a few seconds to take a look at like the syntax and sort of get used to it. If you're familiar with a queue, this should it's essentially the same syntax as a queue if you're familiar with it. Okay, so now we will go on to Prim's algorithm. So we're gonna implement Prim's algorithm for like an adjacency list. So first we set like the weight to 0. We're going to be building up the weight as we go along. The minimum fanning tree weight, I mean. And first we start off by adding like a dummy pair. So that's going to be a weight of 0, and then like the vertex being like the root or whatever vertex you start at, to the min heap. Remember that in our adjacency list for the weighted graph, each element inside the list is a weight and then the adjacent vertex. So that's why we're adding in the pair of weight of 0 and then vertex of root, like at first. And then you go into this loop while the min heap isn't empty. You want to get and remove the highest priority pair, which is going to be, we'll call WV from the min heap. And if you haven't visited vertex V yet, then visit it. You add W to the minimum spanning tree weight. And then for each vertex V prime that's adjacent to V, and if you haven't visited V prime yet, then you want to add the edge, like the edge from V to V prime to the min heap. So that would just be adding like the adjacency, like the weight between V and V prime, and then the adjacent vertex, which would be V prime, to the min heap. And then as this priority queue like loops through, eventually it will become empty, and then you can return the final minimum spanning tree weight. So does anyone have any questions on the pseudocode here? Okay, sweet. No questions. Let's go to the example code. So this is my implementation of Prim's algorithm. We start off by doing like the minimum spanning tree weight to 0. We declare like the vector booleans for like the vertexes that we visited. And then here I do a type def, which is like shorthand for saying I don't want to say pair int of int all the time. So I can just call, if I say PII, that refers to pair of int of int. And I use that to create my priority queue of pairs of ints. And then I push in the pair that is 0 and root, as I stated in the pseudocode. While the priority queue isn't empty, we like get the item, we grab the weight and the vertex from the pair. We check if we visited the vertex. If we have, we add the weight to like our accumulated minimum spanning tree weight. We say that we have visited the vertex. And then this part is a bit confusing. But this is essentially saying for each like adjacent like vertex adjacent to vertex, which is what we got from the priority queue like at the beginning of the loop. If we haven't visited like the vertex inside this edge, then we push that adjacency onto the priority queue. And this is essentially the code for Prim's algorithm. It's a bit hard to understand at first, but I find that tracing it through makes it a lot more intuitive if anyone is still a bit shaky on how Prim's algorithm works. And also going back through the demonstration is also really helpful if anyone needs like extra help with that. All right, Rohit, you want to take over?
Okay, awesome. So let's start. We'll give you about 5 minutes to look at the problem, then I'll go over the sample input, and then we can spend another 5 minutes before I get into the solution. But this problem should look really familiar to the stuff that you've been seeing so far. And hopefully you can implement it quickly as well. So maybe the goal for this problem is also for you to implement it. And hopefully we're able to do that in 10 minutes. But yeah. Okay, so yeah, let's go over, let's try to model the, sorry, let me also go ahead and close the poll. And all right, I guess we can get started now. So yeah, so if you think about it, the way you can model the sample input is exactly what we have seen before, something like a weighted graph. But in this case, we have all possible edges. So, one is connected to all the other villages. So we have sort of what we call a complete graph. And, each of these has an associated weight. For example, village 1 connects to village 2 with a road of distance 1. So we're going to represent that with an edge of weight 1. And so far, so on and so forth. Also notice that the graph is undirected in the sense that distances from village I to village J is the same as the distance from village J to village I. So we can represent it as an undirected graph. And yeah, this is basically just modeling the distances that they gave in the sample input. And if you notice here, we want to find, the problem is basically, it should sound really familiar. And the idea is it basically boils down to finding a minimal spanning tree. And to kind of observe why that is, notice what the problem basically tells you. The problem is telling you that the villages are all connected. So you want to ensure that you have some sort of configuration in which you can visit, where you can always go from one village to another. And second, it needs to be as small as possible. You want this road network to be as small as possible. And we know that's exactly what a spanning tree promises us. A spanning tree is such a thing in an undirected graph, such that you have the least number of edges to connect every other vertex in the graph. But we have another constraint, and that is that we want the distances on each road to be as minimal as possible. And that's exactly the formulation of a minimal spanning tree. So like given a spanning tree, can you find the one with the minimum weight? And that's exactly what the problem is asking for. So we've already seen example code to implement to find an MST to find the weight of an MST using Prim's algorithm. But the problem asks for a little more. It wants us to find the edges of the minimal spanning tree. So we'll have to modify the code a little bit to keep track of that. And maybe before I go over the solution, let me ask you guys. And so in this code, in the original pseudocode where we found the weight of the MS tree, we kept track of this variable MST weight, which we sort of incremented every time we added an edge. But we can get rid of that now, and we can replace that with something else to keep track of what edges. Basically, I'll ask you guys. What should we do to our code so that we can keep track of exactly which edges are included in the minimum spanning tree instead of the weight? So if you guys have any suggestions, I'm happy to hear them. I believe there is more than one way to do this, but I think the way we present here is kind of neat. So does anyone have any suggestions?
Maybe like instead of storing the weight of the edge, you store which vertex it goes to next. Is that a thing that we can do?
Right. It's definitely leading to the right idea, but you cannot ignore the weight, because the weight is the quantity by which the priority queue sorts the edges. So you definitely need to include the weight. But you're right. We can simply expand our pair to become a triple, basically become a three tuple to contain both the weight, the parent edge, or like the parent vertex, basically the vertex where we started from, and all its children, or basically the vertices that it leads to. And that's exactly what that's what we're going to try to do. So in this pseudocode here, yeah, so basically exactly what I said, we can store triples of the form weight, parent, and current. Well, note that the concept of a parent really doesn't exist in such a tree, but by parent, I mean the first vertex that you see, and all the adjacent vertices that you add to it are known as the current vertices. So we modify the code to include triples now, and we're going to go into the construction of these triples in a bit because it's not so obvious in C++. And you basically start with a dummy triple instead of a dummy pair, which is 0 root. And you first remove the front tuple, which includes the weight, v1 and v2. And we'll go into a little more about the distinction between v1 and v2. And just like before, if you have not visited v2, then you visit v2. And this time you print out the edge v1, v2, if v2 is not the root. And the condition here of v2 not being the root is simply to avoid printing out the first edge, which, like, let's say your root is the first vertex is 0, then you want to avoid printing out 0, 0. And that condition basically just allows us to skip printing out anything in the first iteration. And yeah, so instead of keeping track of the weight, we actually print out the edge, which is responsible for adding the minimal edge to our minimum spanning tree. And yeah, and then we proceed as just like always, we find all the adjacent vertices to the current vertex that we're looking at. And these adjacent vertices are denoted by v prime. And for every edge that we haven't visited, for every vertex that we haven't visited, we simply add the following tuple back into the min heap. And this tuple basically contains, the weight of the edge from V2, that is the current vertex that we're looking at, and all its and two of the adjacent vertices. The vertex that we're currently looking at, V2, so that's sort of like our parent, where we came from, and where we're going. So we'll end up going to one of the adjacent vertices, which is V prime. So we add such a tuple to the min heap. And yeah, so far, does anyone have any questions on how we modified the algorithm? Okay, sounds like I was clear. Great. Yeah, so now we can go on code up a solution. The question is, how exactly do we, and this is sort of more of a question of implementation rather than logic, how exactly do we store a three tuple? And C, we've introduced this data structure called a pair that allows you to store two things in C++, but we could naturally extend a pair to store three things by creating a pair of a pair. But I'm going to use this opportunity to introduce something else that has been introduced in C++ 11 called a tuple. And tuples are naturally what you think they are. They allow you to store data of actually even different types and an arbitrary number of them. For example, you can have a three tuple that contains three integers, which is exactly what we're going to need for this problem. And that's basically a natural extension of a pair. A pair is basically just a two tuple. And the syntax is slightly different in the sense that, so firstly, we define a type def triple just so that I can avoid writing tuple int, comma, int, comma, int every single time. And you can basically explicitly initialize a tuple by putting it in curly braces, just like an array. But note that these values can be different and depend on, sorry, let me get my pointer on, depends on how you constructed your triple. So in this case, we constructed our triple by saying that the three values in order are integer followed by an integer followed by an integer. That's exactly how our numbers, our data type should occur in the curly brace notation. Similarly, we can use a function called makeTuple that instead of passing it using these curly brace array sort of notation, you sort of pass it as function parameters. So, if you had a tuple of int, comma, int, comma, int, comma, int, so 4 times, then you could naturally, this function would just be overloaded to have four parameters. And this is sort of where it kind of differs from an array, and it's a little odd. It's a little strange syntax where if you want to access the ith element of a tuple, you have to use this function, this templated function where you say get angular bracket I, and as a parameter pass in the triple. So again, it's zero index. So get 0 temp 1 will return 0 in this case, and get 2 temp 1 will return 2. So yeah, so we're going to use this to create our three tuples because it makes the code a lot simpler to understand. But you can also use a pair of a pair if you think that's more convenient. So the first step of Prim's algorithm, or rather to solve this problem, will be to construct the graph from the given sample input, from the given input. And so we've been using adjacency lists primarily through the graph workshop and the trees workshop. But since every village is connected to every other village, there's really no advantage in using adjacency lists because you're not saving on any space, because every village will contain n-1, will contain n adjacencies. So where the nth adjacency is basically to itself of weight 0. So since we already have to do that, we can simplify our code a little bit and our understanding, or just how the code appears, just by using an adjacency matrix. So over here, we basically have a vector of vectors, and that is basically just a 2D array of some sense. And graph I sub j basically contains the weight of the edge that goes from vertex I to vertex j. And we're also promised that this matrix is symmetric in the sense that the weight of the edge from vertex I to j is the same as the weight of the edge from vertex j to I. And that's promised in the input itself. So really, we don't need to do much about it. We also store an array of booleans, which basically help us mark if you've seen a vertex before that we'll use in Prim's algorithm. Okay, so with that, we can finally get to Prim's algorithm. And it's going to be very similar to what we've seen before, but instead we're going to be working with a three tuple instead of pairs. and we'll basically be printing out values, as we'll come to later, instead of adding to a weight. So the first thing we do is I arbitrarily decide that the root is a 0th, or is the first village or the 0th village, if going by zero indexing. And I, just like before, define my priority queue to be a min heap, and I call this min heap edges. And we can talk about syntax more after the presentation, but this greater triple basically does the reverse of what you think in this case and creates a min heap, just like Alvin talked about. So while there's still edges to look at, sorry, I think something happened. Oh, whoops, I think the animation is kind of messed up. But so while there's still edges to look at, we take out the top edge just like before. And now our edge actually contains 3 quantities rather than 2. So we store each quantity in a separate variable just for convenience. So, the first quantity, or the 0th quantity, is the weight. The first quantity is the vertex we're coming from, or what we call the parent. And the third quantity is the current vertex that we're looking at, or what we call C, which stands for current. And while we haven't seen the current vertex, we mark it as true. And if C is not equal to 0, we print out P plus 1 and C plus 1. So firstly, this condition of checking C is not equal to 0 is just to ignore the first iteration when we've added the first node for the first time. And the P plus 1 and C plus 1 is essentially because the code, or rather the problem statement, has villages indexed by starting from 1. So just to make sure that things make sense with our 0 indexing, we just add 1 to make it 1 indexed. And as soon as we print out the edge that corresponds to the minimum weight as promised by Prim's algorithm, we go ahead and add all of the adjacencies if we haven't seen them before. And that's simply as before, we basically push, in this case, a 3 tuple instead of a 2 tuple that contains the weight of this edge. So from the current node to the adjacent vertex j, the current node itself, and the vertex j. And you kind of might think it's odd that you're checking for visited twice, but it's kind of important because there might be a case where we add an edge, or we add the sort of this 3 tuple for something that we think we haven't seen before, but then we go ahead and add an edge from a different. So a vertex can have multiple edges. So it's possible that we see an edge later on that forces us to include the vertex. And in that case, we no longer want to see any other edge that corresponds to the same vertex. And that's why that's why it's important that we check for visited twice. Okay, with that sort of completes the code. And yeah, and that's pretty much how you solve problem B lostmap. Yeah, does anyone have any questions on the solution or the implementation? Awesome. Okay. If you have any questions that come up later, maybe when you're trying to implement it, or you want to know more about syntax, we're going to be available in the breakout rooms for the next 20 minutes. So we're happy to answer your questions there. But with that, if you could take out some time to fill out the feedback form, we'd really appreciate it. It really matters and really determines what we do for next quarter and the subsequent workshops. So I really appreciate your feedback. And let's just pause here for 2 minutes before we get into the contest. Okay, so with that, we can go ahead and move towards the contest. Here's the link to the contest. Feel free to stay. We'd actually encourage you guys to stay for the next 20 minutes and discuss the contest with us or anything else that you want to talk about. This is kind of where you, I guess, get the most out of our workshops. So would really appreciate it if you stick around. Okay, awesome. Thank you. With that, I'm going to go ahead and stop sharing and